Alright, this is a video on force diagrams. What's a force? A force essentially is any push or pull. A force acts on an object. It can be a contact force or a long-range force. So please pause the video and copy down this table. This table is a list of some of the forces that we will be using throughout the year. A force that we're very familiar with is the force due to gravity. These are the symbols you may be seeing for the force due to gravity. The normal force is a force that is produced by a surface, and it always points perpendicular to that surface. So for example, if you had a table and there was a book sitting on that table would have the force due to gravity, which we would label like that. And the table would be pushing upward with some normal force. However, if the table was at an incline and somehow there was an object on it, the force diagram would look something like this, with a force due to gravity straight down still. But the normal force would be perpendicular to the table. That would be the normal force. The force of tension is produced whenever there is string, cable, rope. And something you should know about the force of tension is that it's the same in all directions. So for example, if we've got a ball that is hanging, that ball would have a force due to gravity downward and a force of tension upward. The applied force is a force that we would use if a person or thing is pulling or pushing on an object. It's essentially the symbol we use in our class when we're not sure what the force is, and it's not any of these other forces. Static friction is one of our three frictional forces. Here are the three frictional forces. They are static friction, kinetic friction, and drag. Static friction is a frictional force that for an object that is not moving. Kinetic friction is a frictional force for an object that is moving. And drag is a frictional force that represents air resistance. All of these are always opposite. All of these forces are always opposites what we call intended motion. Intended motion. And finally, the spring force is a force from a spring or any elastic force. Now, let's look at, as we mentioned earlier, the force of tension is the same in all directions. So if we look at just this region of this rope, the force of tension is actually pulling in every direction, in this direction and in that direction. And it's the same in all directions. Friction, when we look at an object, even from a big view or macroscopic view, the surface looks perfectly smooth, but in a microscopic view, there are irregularities that resist the movement. So for example, if we were drawing the force diagram on this box, we would have the force due to gravity down and a normal force from the floor. And let's say we had a string here that was being pulled, then that would mean we would have the force of tension in that direction. That would therefore mean there would be a force of friction in this direction. Now that force of friction could be two types. If it was actually moving, that would be a force of friction that we would call, actually we would write it like this. that would be static friction or kinetic friction, depending on whether it's moving or not. Static is if it's not moving, kinetic friction is if it is moving. So remember, the force of friction always points opposite the intended motion, opposite the direction the object wants to slide in. Now, let's look at some examples. So what we want to do, we always want to draw a force diagram and a motion map for all of these objects. And remember, we always want our force diagram to show the direction that the object is being pulled. Never pushing, but pulled. So if we look at problem number 2, it says the object slides at constant speed without friction. So if it's, well, let's draw the force diagram. The force diagram would include a normal force up and the force due to gravity down. There's no friction and there's nothing pushing it, so that's the entire force diagram. Let's draw a motion map. The motion map would look like this. It's moving with constant speed. In the picture, it's showing that the object is going to the right. So we would draw our motion map like this, where the velocities are constant. And because the velocities are constant, the acceleration is 0. Now, let's look at number 3. So what we want to do when we solve these is we want to look at this list of symbols. So, and we just want to go down the list. So for this particular object, is there a force due to gravity? Yes. As long as we're near some planet, there's going to be some force due to gravity. Is there a normal force? Yes, there's a surface, so there's going to be a normal force. Whenever there is a surface, there's a normal force. It slows down due to kinetic friction, and since the object is moving to the right, there must be some kinetic friction to the left. Okay, so obviously there's no string. There is not an applied force. There's nothing pushing or pulling it. There is friction, but it's moving, so it's not static friction. There is, therefore, kinetic frictional force. So it points opposite the direction the object is moving in. So there, that would be our, actually we said it was kinetic friction because it's moving. So let's erase this and let's write it this way. The force of friction, so it's kinetic friction. If we want to include some drag force, we could, but the problem doesn't explicitly say there's any drag force, so we could ignore that. And this would be elastic or a spring force, so there's no spring involved. Now, let's look at number 6. In number 6, we go down our list. Is there a force due to gravity? Yes, there is. Is there a normal force? No, because this is our object, and it's not experiencing the force from a surface, so there is no normal force. It's being held by a string, so there's definitely tension, and that tension is pulling it upward. Our motion map includes just a dot showing that there's no velocity and a dot for acceleration showing that there's no acceleration. For number 3, for number 3's motion map, it would look like this. The object is definitely moving to the right, but it's slowing down, so our velocity arrows are getting smaller. Because they're getting smaller, the acceleration arrows point in the opposite direction. Some more examples. Let's look at number 8. Again, we just go down our list. Is there a force due to gravity? Yes, there is. And so we can use any of these symbols. Right now, just to change things up a little bit, I'm going to use mg. We'll talk about why that's the force due to gravity symbol later on. There's no normal force because there is no contact with this particular object. There's definitely tension because I see strings. As a matter of fact, I see two strings. I'm going to use that symbol this time for my string. There's a force of tension in this direction. And there's also a force of tension in this direction. Because we have two different forces of tension, and we know, well, we're not 100% sure, but we want to distinguish the two, we can label one T1 and the other T2. There's no applied force because there's no one pulling or pushing on it. It's not experiencing a static friction or kinetic friction from any surface, and it's not flying through the air, so there's no air resistance and there's no elastic force. In number 9, we have, once again, the force due to gravity. Sometimes that's referred to as the weight, so I'll use that symbol this time. We've got the normal force pointing up and to the right, because remember, it has to be perpendicular to the surface. Here's the surface, and that normal force is pointing in that direction. And there's obviously string pulling it as well. So let's call that F sub t this time. I'm changing the symbols around so that you get used to seeing some of these different symbols. For number 11, actually I'm going to have you guys do number 11. Number 12 we'll do right now. In that particular setup, we've got, you know what, we need to go back and draw the motion maps for number 8 and 9. For number 8, there's no velocity and there's no acceleration. So that's what our motion map looks like. The same is true for number 9. No velocity, therefore there's no acceleration. Number 12 says the object is pulled by force at an angle to the surface. Now, it doesn't tell us specifically, so I'm just going to assume that this is moving. I don't know that for sure, but I'm just going to say that it's moving for the sake of this example. It's being pulled at a force, so I have no idea what this force is. It's string, not 100% sure, so I'm going to use F sub A as the applied force. Okay, that's the applied force. Is there weight? Yes, there is. There's a force due to gravity pointing downward, so force due to gravity. Is there a normal force? It's in contact with a surface, so yes. So, and this is perpendicular to the surface, a normal force like that. Normal force. Is there tension? It doesn't mention a string, so no. We already said that there would be an applied force. Is there static friction? Well, it's moving, so there couldn't be static friction. Is there kinetic friction? It doesn't say there's any friction, so we'll just say there's not. Probably not enough drag force, and there's no spring. Let's look at number 13 now. Number 13, let's go back to 12 and draw its motion map. If it's moving in this direction, one of the things we will find out later on is that the velocity will actually increase. And it will increase in this direction because there's no other force pulling it back in the other direction. And so the acceleration would point to the right. The assumption there is that the box or block stays on the surface. For number 13, we draw its motion maps being pulled upward with a constant speed. So in the upward direction, we would draw a force of tension. In the downward direction, there's a weight or force due to gravity. And that's really it. There are no other forces involved. So let's go ahead and draw our motion map. It says it's being pulled upward with constant velocity. So this is what our motion map would look like. There's no acceleration. Now, we need to be careful with problems like number 13. A mistake that is often made is one in which students see the force pulling in this direction and they want to include that force. Well, that force is not in contact or is not applying a force to this object, to this specific object there. That object is just experiencing this force of tension and that force due to gravity. All right, let's look at number 14. Number 14 is interesting because it has a force, it's showing a force that is pushing instead of pulling. Our force diagram does not use, our force diagram, I'm going to draw it over here off to the side. Our force diagram only shows pulling forces. So since that force is pulling and pushing in that direction, we would show that on our force diagram by pulling in that direction. We're not sure what kind of force it is, so we're going to write down the applied force. Is there a force due to gravity? There is, because there always is, because we're assuming that there's some, that it's on some planet, specifically Earth. Is there a normal force? Yes, because it's in contact with a surface. Is there string? No. We already mentioned that there is applied force. There's no friction. Doesn't tell us that. There's no kinetic friction. We assume that there's not enough drag and it's not connected to a spring. So similar to number 12, we would, because there's an imbalanced force, and we'll learn about this later, the velocity arrows are increasing in this direction, and therefore the acceleration arrows point in the same direction. Let's look at number 15 now. In number 15, choose a different ink color here. In number 15, our force diagram would look like this. There is our object. We have to ask ourselves what force is being applied. Well, there's obviously the force due to gravity. Okay, there's a force due to gravity. Is there a normal force? No, there's no normal force because it's not in contact with a surface. Is there a force of tension? No. Is there an applied force? No. Are there any frictional forces? No. And there's no air resistance, so there's not going to be drag, there's no spring. So this is all we draw for our force diagram for number 15. So let's draw our motion map now. Our motion map, if it starts off being dropped, there would just be a velocity represented by a dot and increasing arrows with acceleration pointing downward. Notice that the only force is a force pointing downward, and it's not a coincidence that the acceleration is pointing in the same direction. We'll talk about that later. In number 17, we have a ball that's rising in a parabolic trajectory. So we go down our list of forces. So our force due to gravity, again, would be straight down. There's no normal force because it's not in contact with the surface. There's no tension because there's no spring, no applied force, no static frictional force, no kinetic frictional force. Is there drag? Maybe a little bit. If you want to include it, that'd be great. It's going opposite the intended motion, F sub D, if you want to include it. And then no static frictional force. 18 is an interesting one. Let's just go ahead and do that one. It's the top of its parabolic trajectory. So obviously there's a force due to gravity. No normal force because it's not in contact with a surface. No string, so there's no force of tension. No applied force. No static or frictional force. No static or kinetic frictional forces. Is there drag force? If there was, there probably wouldn't be enough to matter and no elastic force. So the motion map for 18, let's do 18 first. The motion map for 18 would probably look something like this, where it's at the top of its parabolic trajectory. So if we just did it for that part, it would just be a dot for the velocity. But if we show what happened right before, it would probably be arrows getting larger. And on the way down, velocity arrows getting larger on the way down, but I'm sorry, smaller on the way up, is what I meant to say. And at the very, very top, the acceleration would still be downward. So number 18 is referring to just what's happening at the top. And that's what's happening at the top. The velocity is 0, the acceleration is downward.